Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What would you do with a brain if you had one?
Do? Why, if I had a brain, I could...
Miles per hour.
I could while away
46, 56 degrees.
Well, thanks for coming, everyone. So, first things first, does everyone have an experiment packet? All right. Does anyone not have one? Okay, you're going to miss out if you don't. All right, so we're going to do a few experiments to keep you engaged throughout the 20, 25 minutes that we're going to talk before the movie. And so make sure you have those. Another thing that I'll have a reminder in the slide, don't leave them in your lap. They will melt. So put them somewhere other than your lap. Try not to step on them either if they're on the floor. All right, they're all on the floor or somewhere. Excellent. So what I want to do today is sort of take you through how to build the best chocolate bar that you can build that's going to taste great, that's going to look great, that's going to make the proper sounds. Did you know that chocolate sounds a certain way? Yeah? So we're going to think about that. And then we're going to think about what is the chocolate properties that we see throughout the movie. So Willy Wonka is all about a chocolate factory, right? And so there's tons of chocolate there. There's a river of chocolate. There's trees made out of chocolate. They eat huge things of chocolate. So think about, while you're watching the movie, the properties that we're talking about before the movie and how you can relate those to the chocolate in the film. So let's get started. So here's your experiment pack. You should have all of these things in the pack. And there's a few extras. Again, don't place these in your floor. And we will get started with that. So think about, what's your favorite chocolate? Do you like hot chocolate? M&M's? Reese's? Excellent. What's your favorite chocolate?
Hot chocolate.
Hot chocolate. What about you? Hot chocolate too?
Dark chocolate.
Dark chocolate. That's my favorite too. Ooh, so combinations of chocolate and other things? What about you?
Dark chocolate.
Dark chocolate, yeah. Yes?
M&M.
M&M's. Do you have a favorite color M&M?
Green.
Green? Yeah, those taste good. All right, so what about white chocolate? Easter's coming up, chocolate bunnies. So let's have a warm-up chocolate. And don't just gobble it down, right? Put it in your mouth. Think about how it tastes, how it looks. And my recommendation is to take one of the tiny little chocolate chips. Just one of them, though. And let's get to think about how it tastes. So I'm a scientist. I like to take molecules and rearrange their atoms and put them together and make brand new molecules that have never existed before. And then I study what those molecules can do. Well, there are chocolate scientists, right? So if you want to be a chocolate scientist and develop new chocolates, you can do that. And that's the same kind of thing we're going to be talking about. So here's some of the chocolate scientists throughout the ages. So Nestle and Hershey, these are all familiar names to us, right? Cadbury, Wonka, right? He's not an actual scientist, but we will see him in the movie. And Ghirardelli. So these people spent their lives making the best chocolate that they could make. And we still get to taste all of these today. Let's go here. So what's in a chocolate bar? So if we look at the back of some of the chocolate bars, we can look at some of the ingredients that are in there. So there's sugar, that makes it taste good, right? Cocoa butter. What about more sugar? So if we think about cocoa, this is what a cocoa bean looks like. So I have a few up here if you want to come up after the movie and take a look, or we can just pass these around. But you have one in your packet as well. You have just one cocoa bean. So cocoa beans turn into chocolate, but they're very, very far apart in their nature and their properties. And so we're going to take a path through the cocoa bean all the way to the delicious chocolate bar that we're going to be eating and the chocolate that's going to be seen on the film. So the main ingredients in the chocolate are cocoa particles and cocoa butter. And they have two very different types of molecules. And so we need things that help them mix. So we're going to talk about mixing molecules. We're going to call it right now a mixing helper. We'll talk a little bit more about what it's actually called in a little bit. And where do you think cocoa beans are grown? Yes? South America? Did you have a?
West Africa.
Wow, West Africa. Yes? Jamaica? Anyone else? Africa. All right. So I heard a lot of most everyone got the answer correct. And West Africa is the place where chocolate is made, or cocoa beans come from, right? We can grow cocoa beans in the US too. Does anyone have an idea of where? California? Mexico? Yes? No? Yes. Hawaii. Yes, Hawaii. Why? Because it's really warm. And so most of the chocolate you can see is centered on the equator, and thus it's warm and tropical there, and so cocoa beans grow there. So what does a cocoa bean look like? Does this look like a chocolate bar? No. Right? It doesn't really work either. It wouldn't taste very good either.
Cocoa beans.
Cocoa beans. So why don't you pass this around? Take a look at it. It's about the size of a really small football, maybe a toy football. And they grow on trees. And they look red here. The one that we're passing around has been dried. And if you shake it, you can hear the cocoa beans inside. So that's the same thing that you have in your experiment packet. So once you harvest these cocoa pods, if you look inside, there's all of this flesh inside. It's this white, creamy flesh surrounding the cocoa beans. And then we have to do something called fermentation in order to get the cocoa beans. Does anyone know what fermentation is? Yes.
It is the treatment, or it is when bacteria treat a substance.
And what's produced generally?
Carbon
dioxide.
CO2, carbon dioxide.
Yeah.
And it is used to make cheese, I believe, like, I know wine, I'm not sure about other, like, alcoholic substances. I'm thinking of other, briny things.
Yeah. Anyone else? Have you ever had a fermented food? Yeah, so cabbage can get fermented. Kimchi, that Korean dish, is really good. It's a fermented food. So if you take this, these cocoa pods and empty them out, you can let bacteria and yeast undergo fermentation and remove all of the flesh. They will eat the flesh and help us out in the process of making chocolate. And so here's some yeast, here's some bacteria, and if they start chomping away, right, they're eating all of this flesh, and they're eating it because they like the taste of it. We don't. And they keep eating, and then once dried, the cocoa beans look like this, which is what you have in your experiment packet. So let's see how far we are in our chocolate experiment. So we've started with the pod, and now we've done some fermentation to get the beans out. So let's go ahead and taste the cocoa bean. You might not want to throw the whole thing in your mouth. Maybe bite into it. So while you're trying it, I'm going to tell you what happens after the cocoa beans are dried and roasted. We crush them, and then we get cocoa solids or cocoa powder. If we press them, we can get cocoa butter. So here's what cocoa butter looks like. So while you're eating this, what are some adjectives that you would describe? Does that taste like chocolate? Bitter.
It tastes like a version of bitter chocolate.
A version of bitter chocolate? Very bitter chocolate. Like dark chocolate? Darker than dark chocolate. All right. What does it taste like?
It's very flaky and kind of like rough.
Yeah. So the skin's still on there? Yes. Cooking chocolate, like cocoa powder. Yes, exactly. And that's what these cocoa solids mostly are. And so the bitterness is because we've removed the cocoa butter and they haven't added any sugar yet, right? So we need sugar to make a really good chocolate bar. So let's look at the chocolate in here and let's start making some observations. Scientists always begin experiments with observations. So what does your chocolate look like? Is it shiny? Is it dull? Dull? Is it hard or soft? If it's been sitting in your lap, it's probably soft, right? Is it sweet or bitter? We're not going to get there yet. Soon. But the cocoa bean was bitter, right? So what do you observe? Anyone? Yes?
It's definitely much sweeter and it's much smoother and glossier.
All right. Anyone else? What does it look like? Observations. Yes. Yeah. Anyone else? Yes. Yeah, exactly. All right, so maybe it's crumbly, maybe it's smooth, maybe it melts in your hand. Have you ever heard the phrase melts in your mouth, not in your hand? No? Yeah. You don't watch nearly enough advertisements. No. So what are the properties that we want in our chocolate bar? We want them to be delicious, right? We want them to look pretty. That's typically a very smooth thing, very shiny and smooth. And we want them to snap, right? Chocolate that doesn't snap actually doesn't make us want to eat it. And so that's a bizarre thing to think about. So let's start an experiment. We're going to ask the question, does our chocolate melt in our hand or in our mouth? Or how do we get the two to be different from one another? So here's how the experiment's going to work. You have two types of chocolate chips in your bag. One of them is dark and it's a little flatter, and one of them is lighter and it's a little bit taller. And so the goal here is to put both of them on your tongue at the same time and put them in the mouth and see which one melts first. Yes? Have you already done it?
Yeah.
Oh, wow. Hold on one second. So let's take some time. Think about it. You can close your mouth, make sure all the heat stays in there. So one on each side of your tongue. So which one's melting first?
The milk chocolate definitely melted first.
The lighter one?
Yeah. And then may I make an inference for the little bubble?
Hold on one second. Let's see what everyone else observed. So you had the same, the lighter chocolate. Anyone else have the lighter chocolate? Light? Raise your hand if it was the light chocolate. All right, that's pretty good consensus. Excellent. Did anyone have the dark chocolate melt faster? That's okay too. All right. That doesn't mean you're wrong. That just means that's another data point. So we're just collecting data here. All right, so that one melts faster. So what is melting doing physically? It's going from a solid into a liquid, right? So we're turning our chocolate into a liquid, so that means our chocolate compounds have to be able to turn into liquids. Have you ever seen a chocolate gas before? That'd be cool, but I haven't seen it yet. So what other things would we know that could be transferred from solids, liquids to gases? Water, yes, the classic example, right? So we have ice, which is solid water. We have water, which is water, liquid water. And then we have steam, or just vapor. So that's gaseous water. So we need to think about atoms and molecules. Yes?
I know about this.
You know about this? All right. Well, let's...
The reason that hotter materials melt or evaporate is because the atoms within them, the atoms that make up them, are moving faster, having more collisions, and becoming looser. Therefore, they are spreading apart, so the material becomes less dense. And because they are much looser, they are allowed to, like, spread out.
That's exactly right, but you're giving away the punchline. That's okay. That's exactly right. We're going to get exactly to that point. So let's think about if we zoom down as much as we could with a really high-powered microscope, we could look at atoms inside our chocolate, right? So atoms are the smallest thing that we can see. And if we get a little bit bigger and put atoms together, we can develop molecules. So that's what I work with. So water is a molecule, sugar is a molecule, fats are a molecule, oxygen is a molecule. And then if we put molecules and make really big molecules, we get very complex molecules. And chocolate is composed of those complex molecules. And so going back to our question, what happens when we raise the temperature by putting that chocolate in our mouth? We're going to do an experiment, but a simulated experiment. By looking at this picture here. So here we have an experimental container and we have a bunch of water molecules. So they are frozen right now. They are a solid. So we're going to put energy into them and see what happens to them. All right? What do we expect is going to happen when we put energy or heat into water molecules? Yes?
The particles are going to start to move much more rapidly.
Mm-hmm. Did you have a suggestion? What are molecules going to do? Uh-huh.
Turn into a gas?
Yes. After a solid, they'll go into a liquid first. So here's what we're going to do. So they're moving. So molecules never stop moving, even when they're frozen. That's a crazy thing to think about. We're going to give them a little heat here, keeping the fire underneath it. What's happening? They're moving faster and faster, right? Yeah. So they keep going. They're probably liquids now, right? We keep adding heat. If you can read the temperature from that far, it's very, very hot. And now they've turned into a gas because we've given them enough energy that they're not attracted to one another anymore, and thus they're going to try to move away. They're colliding into each other. They're in a gaseous state. So, when we put energy or increase the temperature of our molecules, we can turn solids into liquids and liquids into gases. So temperature makes molecules move faster. All right? So we call these points within a certain molecule melting and boiling, or freezing or condensing if we're going in different directions. And so if we think about fat, so we have cocoa butter here. It's a solid, right? So are there fats that are liquids, perhaps, that you've seen, right? What's this? Olive oil. It's a fat. It's liquid at room temperature. Butter is mostly a solid at room temperature, right? It can get really soft at room temperature. Shortening is mostly solid. Cocoa butter is very solid. So these are the same type of materials, but they're liquids and solids at different temperatures, which is going to help us make a really good chocolate. Oh, thank you so much. Did everyone get to see the cocoa pod? All right, excellent. So let's look at a molecular structure and think about how these molecules fit together and why they are actually solids. So here's the structure of a fat. So it's a really long, skinny molecule. And they happen to fit really well together. So they can pack very well. So just like everyone's in a seat right next to one another, the seats are packed very, very well. If someone had just thrown a bunch of chairs in the room, that wouldn't be very good packing. So these molecules can pack very well. And so their melting temperatures are quite high. because it takes a lot of energy to get them apart from one another. So the melting point of Crisco, or shortening, is around 176 Fahrenheit. So you have to melt it on the stovetop. But olive oil, it's a molecule that has a kink in it. So it doesn't fit next to one another very, very well. And so, because of this, the melting point is quite low, so 55 degrees Fahrenheit. So you could freeze olive oil, but you'd have to take it outside and put it maybe in a snowbank or something. And so the different fats, because of their structure, are solids and liquids at different temperatures. Does that make sense to everyone? All right, excellent. So what about cocoa butter? It melts at 98.6 degrees. So is it going to be a liquid in your mouth? No. Or a liquid in your hand? A liquid in your mouth, yes. Because the melting point is above the temperature of your hand, but below the temperature of your mouth. So it's going to be a solid in your hand, but a liquid inside your mouth. So when you put your chocolate in your mouth, it's going to melt on your tongue and taste really, really good. All right, so the answer to that question about melting in your mouth, not in your hand, is because of the shape of those molecules, right? And the cocoa butter has a certain shape to it so that it is a solid in your hand and a liquid in your mouth. All right, so cocoa butter and cocoa particles are actually really different substances, and they don't mix very well. And so we need to come up with that mixing helper that we looked at in the very beginning. And if you look on the packages of chocolates, you might see something called soy lecithin, and that's called an emulsifier. So it's, I didn't want to say this, but it's very much like a soap molecule. It's going to help things mix. You don't have soap in your chocolate, I promise you. But it's going to help the two substances mix. So cocoa powder dissolves in water really well, and cocoa powder does not dissolve in oil very well. Remember, oils and fats are very, very similar. And so, just like oil and water don't mix, right? So I have a jar here of oil and water. If I shake it up, they separate in just a bit. Maybe I shook it too hard. Oh, you can see it start to form. Right? So we know that oil and vinegar, salad dressing, doesn't mix very well. So you shake it up right before you pour it on.
I have vinegar.
Yeah? Do you see it? It's separated. So we need something to put in here that allows it to mix thoroughly and pull the oil molecules into the water, pull the water molecules into the oil. And you can do that at home, only under the supervision of your parents, with an egg. So eggs make really good emulsifiers. They're used in all types of cooking to actually bring things that don't mix together. And so if I, I'll clean that up. If you put an egg in here, so we have a separate thing. We have our egg floating at the bottom, but I'm going to break the egg by shaking it. I think. Here we go. So now we've pretty much made one phase completely because we've used the emulsifier to mix the oil and the water together. There's molecules inside the egg that will actually cause the two to mix very thoroughly and keep them mixed for a much longer period of time. So we'll leave this here and see how long it takes to separate. All right, so if we want to mix things together, we need to use emulsifiers. So we think about cocoa solids, they're called hydrophobic substances. So the word hydro means water, right? So hydrant, like a fire hydrant, hydroponic, hydroelectric, water in all of these things. Cocoa butter is a substance called a hydrophobic substance. So it it also has water in it. Philic, in this case, hydrophilic means like, so water likes or likes water. So you can think about words like Philadelphia or chocophile. And phobic means fear or dislike. So hydrophobic means it doesn't like water. And so the cocoa butter doesn't like water, just like the oil doesn't like water, and so forth. And so we're going to, funny animation, right? Hydrophilic means it likes water. Hydrophobic means it repels water. So we want something that can bring these two together, and we need a substance called an amphiphilic substance. So it's sort of like the fat, or the hydrophobic substance, and sort of like the water, or the hydrophilic substance. So it has both parts in the same molecule. So if we put those together and use the amphiphilic substance, like the emulsifier, we can mix those two together. So here's our separate species. We add our emulsifier, and we can see that they are mixed very, very thoroughly, just like your chocolate bar. All right. So on to our final experiment. So you have two chocolate bars. One has the regular packing. The other one has a bright green label on it. So I want you to open both of them and compare them visually. What do they look like? What are the differences in the color? And I also want you to take them and snap them in between your fingers and listen to what happens. That's okay. So listen for the snap. All right. Did we hear the snap on the one without the green label? Yeah. Yes. Did we hear the snap of the one with the green label? No. What happened? It was... It melted? Did you keep it in your lap? So it's really soft, right? It bent. So what's the difference between those two? One is hard, one is soft. Which one would you prefer to eat? The one without the green label. Would anyone else like to eat the one without the green label over the one with the green label? Yeah. So the sound that chocolate makes is actually really enticing, right? So let's think about how that sound is made. So you broke it. This is probably what it looks like, right? Crumbly, it bent really weird. So let's think about what makes the chocolate glossy and snap when it breaks. I'm not going to show you this. But the process going from a liquid to a solid is called a crystallization. And that's just like you're freezing ice cubes. That is water crystallizing into a solid. And so the same thing happens with chocolate. Yet in chocolate, so if we use these to represent chocolate, chocolate can form certain structures like this, where they're all very packed well together, or differently packed substances. Actually, chocolate has 7 different structures it can form. And so when you heat chocolate up and let it cool down, there's 7 options for it to fall into or crystallize in. And depending on this packing, you're going to get the really good snap, the really glossy finish, or the really nasty, very bent, crumbly chocolate. And so if you're a really bad chocolatier or chocolate scientist, you're not going to make very pretty chocolate. And so a lot of your time is spent developing the process to make this chocolate correct. And so the good crystal form, the good packing of the chocolate is going to produce a really pretty chocolate. It's going to be very, very shiny. It's going to snap. And the bad is going to look like it's dusty or moldy. And that's not going to entice anyone to buy your chocolate. So you'll go out of business. I know. So if you get chocolate that looks like this in the package, it can mean a bunch of different things. It can mean that your chocolate's been sitting out too long. It's not stored properly. or the chocolatier didn't do a good job of making sure that crystalline structure is properly formed. And so, you need to spend a lot of time making sure that those molecules within the chocolate are actually going to pack just well enough so that you get your really pretty chocolate. So, recapping on what makes cocoa beans into delicious chocolate bars, right? We have to have the proper melting temperatures of the different materials where we're mixing the fats and the other substances, the cocoa nibs or cocoa powder. We need to combine emulsifiers so those two things mix together. So we talked about the mixing, right? You see my solution still hasn't separated. That's a good thing. And then our last experiment was looking at the crystallization of the particular chocolate bar, where we needed the exact crystal structure in order to get a really tasty and visually appealing chocolate bar. So, as you watch the movie, look at the different types of chocolate that are throughout the movie and think about how you would mix those two components together along with sugar and emulsifiers to make the type of chocolate that you see throughout the film. So with that, thanks to Images Cinema and to the sponsors, and thanks for listening. I hope you got something out of this.